Hello everyone. This is the fourth video in the lecture series on linear transformation. Here I am going to explain kernel and image of a linear transformation. Let us take a linear transformation T from V to U. V and U are two vector spaces over a field F. Kernel of T is denoted as this. It is set of all those vectors from V which are mapped to the zero vector of U. Okay, set of all those vectors for which t of v equal to 0 is called as kernel of the transformation. Image of the transformation is nothing but set of all u belongs to u, the vectors of the vector space u, such that there exists v belongs to v for which t of v equal to u. Means you have to collect all those images from this second vector space. Those images are having some preimage in the domain. Okay. Then such vectors form image of the transformation. See, for example, I had taken the transformation t of x comma y equal to y comma minus x. This is rotating plane by 90-degree clockwise. Rotating plane by 90-degree clockwise. This is the transformation from r square to r square. This is the linear transformation from r square to r square. Here the domain is r square, codomain is also same. It is a linear operator because when the first and the second vector space both are same, then t is a linear operator. So anyway, take this linear transformation which rotates the plane by 90-degree clockwise. So we have to find out kernel of this transformation. So kernel of t is set of all those vectors which are in r square such that t of v equal to 0. Those vectors which map to 0 all come under this kernel of t, this set. All those vectors which get mapped to 0 will come and reside in this set kernel of t. Okay, so here set of all v belongs to r square such that t of v equal to 0 means t of x comma y equal to 0. So what is t of x comma y? V belongs to r square such that t of x comma y is nothing but y comma minus x equal to 0. This is nothing but L right here. V means I have taken it as x comma y belongs to r square such that y comma minus x equal to 0 means 0 comma 0. 0 of the second vector space is nothing but it is origin of r square. So y equal to 0, x equal to 0. Only one possibility. Therefore, this gives you the set containing only one element 0 comma 0. You know that when you rotate a plane by 90-degree, only 0 vector goes to 0. No other vector goes to 0. Therefore, kernel of this transformation, kernel of t equal to set containing 0. For any linear transformation, kernel of any transformation is always non-empty because 0 vector or the 0 element of the first vector space should go to the 0 element of second vector space as per the definition of linear transformation. So it is always non-empty, but this transformation exclusively has only 0 vector as its element in the kernel t, means only 0 vector gets mapped to 0, no other vector is getting mapped to 0. So kernel of t equal to set containing only 0 comma 0. Similarly, you have to find out image of t. Image of t equal to set of all u belongs to u, that is second vector space, u belongs to r square such that there exists v belongs to v for which t of v equal to u. Okay. Now this is equal to set of all u belongs to r square. So you can take u as p comma q belongs to r square such that there exists v belongs to v, there exists v belongs to v for which t of v equal to u, which is nothing but p of p comma q. So let us simplify this. Set of all p comma q belongs to r square such that there exists v belongs to v for which T of B, T of x comma y. Okay, I will take V as this V as x comma y. Okay, T of x comma y equal to P comma Q. Correct now? So this is equal to P comma Q belongs to R square such that there exists V belongs to V, for which T of x comma y is y comma minus x equal to P comma Q. Okay, this implies from this P equal to y and Q equal to minus x. So this is y comma minus x belongs to R square. All those vectors y comma minus x. Image is of the form y comma minus x belongs to R square. So image contains all those vectors from R square which are of the form y comma minus x. This is nothing but whole space R square. Image of this transformation is whole space R square. This means that every element of R square has a pre-image in R square under the transformation T. Hence you will get image of this transformation as the whole space R square. Now take one more example to understand kernel of the transformation and the image of the transformation. See here, T from R cube to R cube be the projection map. That is projection of a vector V into the xy plane given by T of x comma y comma z equal to x comma y comma 0. We need kernel of this transformation, which is set of all V belongs to R cube such that T of V equal to 0. So this is equal to V belongs to R cube such that T of V, T of x comma y comma z equal to 0 comma 0 comma 0, because 0 of R cube is 0 0 0. This is equal to V belongs to R cube such that what is T of x comma y comma z? X comma y comma 0 equal to 0 comma 0 comma 0. Okay. So this implies set of all V belongs to R cube such that x equal to 0, y equal to 0. Set of all those vectors for which x coordinate is 0, y coordinate is 0. This is nothing but equation of z axis. For a z axis, both x coordinate and y coordinate is 0. Therefore, the entire z axis is the kernel of this transformation. The transformation is nothing but it is a projection map, x axis, origin, y axis and z axis like this. So any vector here you have x, y, z, then that gets mapped to x comma y comma 0. It comes to the xy plane. So what happens? All those vectors which are on the z axis, negative as well as positive, they will be mapped to 0. So you have to collect all those vectors which are mapped to 0. So all the vectors which are on the z axis get mapped to 0, because suppose if you take 0 0 1, okay, that is a vector on the z axis 0 0 1, where it goes to 0 0 1 goes to 0 0 0, because z coordinate automatically gets mapped to 0. Whatever other values, it is already 0. So entire z axis collapses and it gets mapped to 0. This whole z axis gets mapped to 0. So this becomes the kernel of T. Okay, kernel of T means whole z axis, entire z axis. Now similarly, image of this transformation is set of all U belongs to R cube such that there exists V belongs to R cube for which T of V equal to U, means U is the pre-image of some element of the domain. So that we have to find out. U belongs to R cube. You take it as x, y, z only such that T of V equal to U. Okay, this is equal to, you can take here as A, B, C, because x, y, z is already in the transformation. So set of all A, B, C belongs to R cube for which T of B. What is T of x, comma y, comma z? X, comma y, comma 0 is equal to A, comma B, comma C. So this implies, see here, set of all A, comma B, comma C belongs to R cube such that C equal to 0. Correct now. So C equal to 0 from this. When you equate these two, whatever may be the values of A and B, but this remains constant, C equal to 0. The third coordinate 0 means it is in which plane? X, Y plane. Okay. XY plane, this includes all those points A, comma B, comma C, for which the condition is C equal to 0. For any point in space, if the third coordinate is 0, then that point must be in the xy plane. So image of this transformation is entire xy plane, and the kernel of this transformation is z-axis. Meaning is the entire z-axis gets mapped to 0, and image of T means here all the vectors in R cube get mapped to xy plane. But see here in the previous case, there was no condition or restriction on these x and y. So hence it goes to the entire plane R square. So in this case, we got C equal to 0 due to which xy plane I got in the second example. Whereas in this example, there were no restrictions on the coordinates x and y. So x and y are written as y comma minus x. So that is nothing but whole space R square. See here, if T is a mapping from B to U, linear transformation from B to U, then kernel of T will be a subset of this first vector space V, means domain here. Image of T is a subspace of the second vector space, which is nothing but codomain. So you have to collect kernel of T is nothing but it is a part of this vector space. You have to collect all those vectors which get mapped to the 0 of this second vector space. Okay. Similarly, image of T means nothing but it is some vectors in the vector space U which are having the pre-image. So including 0 also, some image of T. Image of T can be equal to the entire space U, or image of T can be a subspace of, can be a subset of U. Okay. You have to take all those elements which are having the pre-image. Means here every element gets mapped to some element, correct? No. So the mapped versions you have to take all of them and you have to form the image set. See, for example, if there is a transformation T of x comma y from R square to R square, where every element gets mapped to 0, then what is its kernel? Kernel of T is nothing but the whole space R square, because whole space R square to R square, okay, T is a transformation. This whole vector space gets mapped to only one element, which is 0 comma 0. So kernel of T is nothing but whole space R square, whole plane R square here. And image of T means which element has got the pre-image. So it is only 0 comma 0. Only this 0 comma 0 is having the pre-image. That is what the meaning of image of T. But in the second case, T of x comma y equal to y comma minus x, in this case, where here you had a rotation of a plane by 90 degree. So R square to R square, here only 0 vector was getting mapped to 0. So this is the kernel of T, whereas the entire space here, so image of T is nothing but the entire codomain is having a pre-image. Suppose if you take 1 comma 2, here take 2 comma minus 1, that goes to 2 comma 2 comma minus 1 is having the pre-image. Suppose here you have 1 comma 2, so the pre-image of 1 comma 2 is minus 2 comma 1, because this goes to 1 comma minus of minus 2 plus 2. Then p equal to y and q equal to minus x. Hence you will get the whole space R square as its image. In one more example, T of x comma y comma z equal to x comma y comma 0. Here it was a mapping from R cube to R cube. So the entire z axis, that is 0 comma 0 comma z, all these get mapped to 0 comma 0 comma 0. Okay. So whole z-axis gets mapped to 0 comma 0 comma 0. Then xy plane. All images are in the xy plane. No other element you will get as an image, because the look here, image means Image of the T transformation is nothing but range of that transformation. Range means you have to look the output. All possible outputs here, all possible outputs are of the form x comma y comma 0, which are nothing but points in xy plane. So remember like this xyz is the input, xy0 is the output. So if you collect all outputs, then you will get the image of the transformation. If you collect those inputs which map to 0, then you will get the kernel of the transformation. And one more thing to remember is kernel of T is a subspace of V, and image of T is subspace of T. Okay, kernel of T is not just a part of V, it is it itself, that itself forms a vector space. So it is a subspace of V, and image of T is a subspace of T. So if kernel and image are subspaces, then they act as vector spaces independently. Therefore, you will definitely have number of elements in the basis of the vector space. So that is nothing but dimension of kernel T and dimension of image of T, and what does it is called. Hence it leads to rank nullity theorem. So we shall see that in the next video. Hope you understood this concept. Thank you for watching.